we've seen in the last several videos, you start off with any crazy distribution. It doesn't have to be crazy. It could be a nice normal distribution. But to really make the point that you don't have to have a normal distribution, I like to use crazy ones. So let's say you have some kind of crazy distribution that looks something like that. It could look like anything. So we've seen multiple times you take samples from this crazy distribution. So let's say you were to take samples of, let's say n is equal to 10. So we take 10 instances of this random variable, average them out, and then plot our average. We plot our average. We get one instance there. We keep doing that. We do that again. We take 10 samples from this random variable, average them, plot them again. You plot it again. And eventually, you do this a gazillion times, in theory, infinite number of times. And you're going to approach the sampling distribution of the sample mean. And our n equal 10, it's not going to be a perfect normal distribution, but it's going to be close. It would be perfect only if n was infinity. But let's say we eventually, all of our samples, we keep, if we get a lot of averages that are there, that stacks up there, that stacks up there, and eventually we'll approach something that looks something like that. And we've seen from the last video that, one, if, let's say we were to do it again, and this time let's say that n is equal to 20. One, the distribution that we get is going to be more normal. And maybe in future videos, we'll delve even deeper into things like kurtosis and skew. But it's going to be more normal, but even more importantly, or I guess even more obviously to us, and we saw that in the experiment, it's going to have a lower standard deviation. So they're all going to have the same mean. Let's say the mean here is, I don't know, let's say the mean here is 5. Then the mean here is also going to be 5. The mean of our sampling distribution of the sample mean is going to be 5. And it doesn't matter what our n is. If our n is 20, it's still going to be 5. But our standard deviation is going to be less than either of these scenarios. And we saw that just by experimenting. It might look like this. It's going to be more normal, but it's going to have a tighter standard deviation. So maybe it'll look like that. And if we did it with a even larger sample size, let me do that in a different color. If we did that with an even larger sample size, n is equal to 100, what we're going to get is something that fits the normal distribution even better. And we take 100 instances of this random variable, average them, plot it. 100 instances of this random variable, average them, plot it. And we just keep doing that. If we keep doing that, what we're going to have is something that's even more normal than either of these. So it's going to be, a much closer fit to a true normal distribution. But even more obvious to the human eye, it's going to be even tighter, so it's going to be a very low standard deviation. It's going to look something like that. And I'll show you that on the simulation app in the next, or probably later in this video. So two things happen. As you increase your sample size for every time you do the average, two things are happening. You're becoming more normal, and your standard deviation is getting smaller. So that the question might arise, well, is there a formula? So if I know the standard deviation, so this is my standard deviation of just my original probability density function. This is the mean of my original probability density function. So if I know the standard deviation, and I know n is going to change depending on how many samples I'm taking every time I do a sample mean. If I know my standard deviation, or maybe if I know my variance, right? The variance is just the standard deviation squared. If you don't remember that, you might want to review those videos. But if I know the variance of my original distribution, and if I know what my n is, how many samples I'm going to take every time before I average them in order to plot one thing in my sampling distribution of my sample mean, is there a way to predict what the mean of these distributions are? And so the standard deviation of these distributions. And so you don't get confused between that and that, and let me say the variance. If you know the variance, you can figure out the standard deviation. One is just the square root of the other. So this is the variance of our original distribution. Now, to show that this is the variance of our sampling distribution of our sample mean, we'll write it right here. This is the variance of our mean, of our sample mean. Remember, our true mean is this, that the Greek letter mu is your true mean. This is equal to the mean, while an x with a line over it means sample mean. Sample mean. So here what we're saying is this is the variance of our sample means. Now this is going to be a true distribution. This isn't an estimate. There's some, if we magically knew this distribution, there's some true variance here. And of course the mean, so this has a mean. This right here, we can just to get our notation right, this is the mean of the sampling distribution of the sampling mean. So this is the mean of our means. It just happens to be the same thing. This is the mean of our sample means. It's going to be the same thing as that, especially if we do the trial over and over again. But anyway, the point of this video, is there any way to figure out this variance, given the variance of the original distribution and your n? And it turns out there is. And I'm not going to do a proof here. I really want to give you the intuition of it. And I think you already do have the sense that every trial you take, if you take 100, you're much more likely, when you average those out, to get close to the true mean than if you took an n of 2 or an n of 5. You're just very unlikely to be far away, right, if you took 100 trials as opposed to taking 5. So I think you know that in some way it should be inversely proportional to n. The larger your n, the smaller a standard deviation. And actually, it turns out it's about as simple as possible. It's one of those magical things about mathematics. And I'll prove it to you one day. I want to give you a working knowledge first. In statistics, I'm always struggling whether I should be formal and giving you rigorous proofs, but I've kind of come to the conclusion that it's more important to get the working knowledge first in statistics. And then later, once you've gotten all of that down, we can get into the real deep math of it and prove it to you. But I think experimental proofs are kind of all you need for right now, using those simulations to show that they're really true. So it turns out that the variance of your sampling distribution of your sample mean is equal to the variance of your original distribution, that guy right there, divided by n. That's all it is. So if this up here has a variance of, let's say this has up here has a variance of 20. I'm just making that number up. Then and then let's say your n is 20. Then the variance of your sampling distribution of your sample mean for an n of 20, well, you're just going to take the variance up here, your variance is 20, divided by your n, 20. So here, your variance is going to be 20 divided by 20, which is equal to 1. This is the variance of your original probability distribution, and this is your n. What's your standard deviation going to be? What's going to be the square root of that? Right? Standard deviation is going to be the square root of 1. Well, that's also going to be 1. So we could also write this. We could take the square root of both sides of this and say the standard deviation of the sampling distribution of the standard deviation of the sampling distribution of the sample mean. It's often called the standard deviation of the mean, and it's also called, I'm going to write this down, the standard error of the mean. Standard error of the mean. All of these things that I just mentioned, these all just mean the standard deviation of the sampling distribution of the sample mean. That's why this is confusing, because you use the word mean and sample over and over again. And if it confuses you, let me know. I'll do another video or pause and repeat or whatever. But if we just take the square root of both sides, the standard error of the mean, or the standard deviation of the sampling distribution of the sample mean, is equal to the standard deviation of your original function, of your original probability density function, which could be very non-normal, divided by the square root of n. I just took the square root of both sides of this equation. I like to remember this, that the variance is just inversely proportional to n. And then I like to go back to this, because this is very simple in my head. You just take the variance divided by n. Oh, and if I want the standard deviation, I just take the square roots of both sides, and I get this formula. So here, the standard deviation, when n is 20, the standard deviation of the sampling distribution of the sample mean is going to be 1. Here, when n is 100, well, our variance here, when n is equal to 100, so our variance of the sampling mean of the sample distribution, or our variance of the mean, of the sample mean, we could say, is going to be equal to 20, this guy's variance, divided by n. So it equals, n is 100, so it equals 1/5. Now, this guy's standard deviation, or the standard deviation of the sampling distribution of the sample mean, or the standard error of the mean, is going to be the square root of that. So 1 over the square root of 5. And this guy's be a little bit under 1/2 standard deviation, while this guy had a standard deviation of 1. So you see it's definitely thinner. Now I know what you're saying. Well, Sal, you just gave a formula. I don't necessarily believe you. Well, let's see if we can prove it to ourselves using the simulation. So I'll, just for fun, let me make I'll just mess with this distribution a little bit. So that's my new distribution. And let me take let me take two things it's easy to take the square root of, because if we're looking at standard deviation. So let's take an n of 16 and an n of 25. And let's do 10,000 trials. So in this case, every one of the trials, we're going to take 16 samples from here, average them, plot it here, and then do a frequency plot. Here, we're going to do 25 at a time, and then average them. I'll do it once animated just to remember. So I'm taking 16 samples, plot it there. and I take 16 samples as described by this probability density function, or 25 now, plot it down here. Now, if I do that 10,000 times, what do I get? What do I get? All right, so here, just visually, you can tell just when n was larger, the standard deviation here is smaller. This is more squeezed together. But actually, let's write this stuff down. Let's see if I can remember it here. Here, n is, so in this random distribution I made, my standard deviation was 9.3. I'm going to remember these. Our standard deviation for the original thing was 9.3. And so standard deviation here was 2.3, and the standard deviation here is 1.87. Let's see if it conforms to our formula. So I'm going to take this off screen for a second, and I'm going to go back and do some mathematics. So I have this on my other screen so I can remember those numbers. So in the trial we just did, my wacky distribution had a standard deviation of 9.3. When n is equal to, let me do this in another color. When n was equal to 16, just doing the experiment, doing a bunch of trials and averaging and doing all the things, we got the standard deviation of the sampling distribution of the sample mean, or the standard error of the mean. We experimentally determined it to be 2.33. And then when n is equal to 25, we got the standard error of the mean being equal to 1.87. Let's see if it conforms to our formulas. So we know that the variance, or we could almost say the variance of the mean, or the standard error, the variance of the sampling distribution of the sample mean is equal to the variance of our original distribution divided by n. Take the square roots of both sides, and then you get standard error of the mean is equal to standard deviation of your original distribution divided by the square root of n. So let's see if this works out for these two things. So if I were to take 9.3, so let me do this case. So 9.3 divided by the square root of 16, right? N is 16. So divided by the square root of 16, which is 4, what do I get? So 9.3 divided by 4. Let me get a little calculator out here. Let's see. We have, let me clear it out. We wanted to divide 9.3 divided by 4. 9.3 divided by our square root of n, n was 16, so divided by 4, is equal to 2.32. 2.32. So this is equal to 2.32, which is pretty darn close to 2.33. This was after 10,000 trials. Maybe right after this, I'll see what happens if we did 20,000 or 30,000 trials, where we take samples of 16 and average them. Now let's look at this. Here, we would take 9.3. So let me draw a little line here. Maybe scroll over. That might be better. So we take our standard deviation of our original distribution. So just that formula that we derived right here would tell us that our standard error should be equal to the standard deviation of our original distribution, 9.3, divided by the square root of n, divided by the square root of 25, right? 4 was just the square root of 16. So this is equal to 9.3 divided by 5. And let's see if it's 1.87. So let me get my calculator back. So if I take 9.3 divided by 5, what do I get? 1.86, which is very close to 1.87. So we got in this case 1.86. 1.86. So as you can see, what we got experimentally was almost exactly, and this was after 10,000 trials, of what you would expect. Let's do another 10,000. So you got another 10,000 trials. Well, we're still in the ballpark. We're not going to, maybe I can't hope to get the exact number, rounded or whatever. But as you can see, hopefully that'll be pretty satisfying to you, that the variance of the sampling distribution of the sample mean, the variance of the sampling distribution of the sampling mean, is just going to be equal to the variance of your original distribution, no matter how wacky that distribution might be, divided by your sample size, by the number of samples you take for for every basket that you average, I guess is the best way to think about it. And sometimes this can get confusing because you are taking samples of averages based on samples. So when someone says sample size, you're like, is sample size the number of times I took averages or the number of things I'm taking averages of each time? And it doesn't hurt to clarify that. Normally when they talk about sample size, they're talking about n. And at least in my head, when I think of the trials as you take a sample size of 16, you average it, that's one trial, and you plot it. Then you do it again, and you do another trial, and you do it over and over again. But anyway, hopefully this makes everything clear, and then you now also understand how to get to the standard error of the mean.